Hello to everybody. So I hope you hear me. So I will speak about dynamical systems, which is an area of mathematics, and a tool which recently, I mean, for last 50, 60 years has been a lot used in dynamical system, which is renormalization. So I normally work in Marseille, but today I'm calling to you from Irkutsk in Russia, near the Lake Baikal. So here it is 7 o'clock in the evening. I don't know how much time it's at your place. I imagine different times. So let me explain why I'm calling you from Irkutsk. It's not really related to dynamical systems, at least not in a direct way. I'm working on a project which is called Mathematica, which means math in Russian, about Russian women in mathematics who are researchers, professors, administrative staff of universities and of different labs. And we are traveling along Russia. We started in Khabarovsk, which is a city on the southeast of Russia, and we are going to St. Petersburg. You can see our route on the map, and we will speak with different heroines of the trip, and hopefully do an exhibition for the next year International Congress of Mathematicians. Maybe you have heard of this Congress. It's an event which is happening each 4 years, and where there are many conferences and many mathematicians come to this event. One of the features of this Congress is that Fields medals are given out at this Congress, like Nobel Prizes in mathematics. And next year it will be in St. Petersburg. So that's why this exhibition, I hope, will have a good welcome there at this Congress. And I just wanted to say, if you are interested in this project, you can look at it and follow us around. We have an Instagram account which is called Mathématiques Vagabondes, which means vagabond mathematics in French, and a site where we tell the stories and like follow our trip in real life. So now we are on the second stop in Irkutsk. And I'm very happy to do this project, but I'm especially happy to speak about mathematics even in these Siberian conditions we are now at. So mathematically, I would like to speak to you about renormalization and dynamics, as I said. So dynamical systems is a domain of mathematics which is interested in movement, in modelization of movement, and in understanding of it. This is a very general description, but I think you already had a talk by Yuri on the subject. And it's quite a new subject. It started in the end of 19th century with Poincaré and Birkhoff. New, it depends, of course, not respect with our lives, but with respect to the life of mathematics, which has millennaries of years old. But renormalization, even in this new domain of dynamical system, is also quite a new idea, and it's one of the main techniques in dynamical systems today. In some sense, it's becoming a domain in itself, and it really changed the way we do dynamical systems today. So I want to give you an idea of what is renormalization, hopefully convince you that it is very useful for the understanding of dynamics of movement of some systems, and at the same time to give you an idea of questions that one is interested in when studying dynamics. So I will formulate some questions and answer to them with the help of renormalization. So the main ideas about renormalization that I want to share with you is that to renormalize is to transform your problem, some problems that you have, into a problem of the same kind. But one can imagine that you won't get anything from transforming a problem to something which resembles it a lot, but renormalization's force is that you will actually get something from it. And the second idea about renormalization is that it can bring some universality to your dynamical, to the behavior of your dynamical system. We will not study one movement, but a class of movements, and different movements, different dynamical systems will have similar behavior, because all of these behaviors will be governed by some bigger dynamical system, in some sense meta-dynamical system, in the space of this movement itself, which is a renormalization operator. So a renormalization operator is a new dynamical system, but which governs the dynamical systems themselves. So I will give you two examples of this renormalization today. So you will have a precise image and not this big, even though very beautiful words, philosophical words. So a practical goal of my talk today is to explain this picture you see on the screen. You see that this is some kind of diagram. It's not a graph, but it's kind of a picture, which seems very complicated because there are some lines, smooth lines that meet, kind of bifurcate, branch into some other rivers, and then do something very, very, very complicated. It seems very complicated, and I will explain how this picture is related to the study of very simple dynamics, very simple map, which is a quadratic map, mapping x to ax multiplied by 1 minus x, where x is just a number between 0 and 1, and a is some parameter. So the idea is that very simple dynamics gives, in some way, very complex pictures in some situations. So before going to this quadratic dynamics, let us start with linear maps, and let me remind you what dynamical systems are. So the first example of this talk, there will be two examples. So the first example is circle rotations. So what is a dynamical system? A dynamical system is just a map from some space to itself, some movement in some space. And the goal of people who are interested in the study of dynamical systems is to understand its iterations. So you take some point in your space. You can think, for example, of a plane, of a line. Today we will be working a lot when x is just an interval or a circle, one-dimensional space, and your point moves in some way. So we will consider orbits of this point, which is the point itself that I denote by x, its image by your map f of x, the image of x, so that I write f of x, etc., etc. So you look where the point goes under the iterations of your map. For example, if you have a circle rotation, so I write it as x goes to x plus alpha modulo 1. Modulo 1 means that if the number is between 3 and 4, what is interesting to me is only its fractional part. I just take minus 3 from this number. I'm not interested in its integer part. I'm only interested in its fraction part. So I'm moving on a circle. I'm rotating by this angle alpha on a circle. I suppose that the circle has length 1. So you see, I drew here the orbit, the beginning of the orbit of x. X, f of x, f square of x, f cube of x, f4 of x, f5 of x. Maybe on the picture it's not perfect, but the distances are all equal to alpha on the circle. So the word orbit comes from the history of dynamical systems, because the first dynamical systems were related to the planetary motion. So this word stayed to speak about this set of points in x, f of x, f of x, etc. This set can be infinite, or it can be finite, or it can be also one point. For example, if f of x is equal to x, the orbit of your point is just the point itself, and we call such points fixed points of your map. The points for which fn of x, so n iterations of x, are equal to x are called periodic points with period n, and other points that have infinite orbits don't have a special name. So we have these three possibilities. So let us look what happens for rotations. Rotation, in some sense, is a very simple dynamical system, because all points have the same destiny, very close destinies, because if one point moves in some way, another point just mimics its behavior, but shifted by alpha. So one can prove, and it's very easy exercise, maybe it's clear for you how to prove it, is that if a rotation is a periodic map, so meaning that all of its points are periodic, all of its points come back to themselves after some number of iterations only if alpha is rational. If and only if is alpha is rational number. So I have proven it in one direction. So you see that if alpha is rational, of course, x plus p over q added q times, it's just x plus p, where p is some integer number. And so it's the same thing as x, since we are living on the circle. P is equal to 0 modulo 1. And the other direction is not very difficult either. You can do it as an exercise. So we have our dynamical system, which is periodic if and only if alpha is rational. And if alpha is irrational, we can think what happens to the orbit of the point. One can show that in this case, the orbit is very different. It will fill the circle in a dense way. Dense means the following, that the orbit, the points of the orbit come into any interval on the circle. If you choose a very, very small interval on the circle and you wait enough time, an orbit of some point you have chosen will necessarily come into this interval you've chosen. So the pictures are very different. The orbit for a rational map looks something like this, like a discrete final set, and the orbit of a irrational rotation looks from far away, it just looks like a circle. So you see that the dynamics of rational and irrational rotations are very different. But say we take two different irrational rotations. Are they different? Are they the same? Okay, in this simple theorem, they are the same. The orbits are dense. But in some ways, we can distinguish two of irrational rotations, for example, by saying that the order in which the orbits of points are placed can be different with respect to the angle alpha. You see that if you take some few number of iterations, the points are put in a linear order. X is before f of x is before f squared of x, etc. But at some moment, your orbit jumps over the initial point, and it's not very clear in which order the iterations are placed. And of course, for different irrational numbers, this order is not the same. And one could be interested in distinguishing this order. And I will now explain how this kind of questions can be answered. And for this, I will introduce renormalization. But let me stop for a while and ask if you have some questions, just to be sure that we are on the same wavelength, so to say.
So let me remind all participants that the questions should be typed in the question section on GoToWebinar.
And while you are thinking about questions, let me ask you a question. Maybe you can also write me answers for this irrational rotation. If I take the interval 0 alpha, so I take a irrational rotation of angle alpha, or actually even rational rotation of angle alpha, and I look at the first return map on the small 0 alpha. Small return map, first return map means the following, that small interval, you take some point and you look when it comes the first time back to this interval 0 alpha. So for example, on this picture, 3 times it comes back. R alpha of x is somewhere outside, R alpha squared of x is somewhere outside, and then T of x, so actually x plus 3 alpha, is back to the interval. And my question is, what is the map that it's in some way induced by the separation on 0 alpha? If I look only on 0 alpha and I look on the map T, what is this map? What can we describe it in some simple way? So this is my question for you, but please give me some questions or just say it's clear, please continue.
For the moment, I see no questions, and I assume, there's at least one comment, several, saying it's very clear, no problem.
Good, okay, so I continue. So maybe someone can say the answer to this question before I start explaining how I can get it, or maybe a guess. What do you think the first return map is? So of course here, if I take a point very close, it will come back after the same number of iterations. So one feels that this first return map is kind of piecewise continuous in some sense, that there are maybe only a finite number of break points, that there are maybe many points which have the same kind of future. Are there some answers maybe, or maybe guesses?
Not for the moment. It may take some time for them to type them, so I don't know.
So if you have a guess while I'm explaining, please write what you think. So let me answer my question. I hope the question is clear. So we have a
there's a guess now. Should I say it now?
Yes, please.
Should I? So the by Stupacharkov saying that T of alpha should be 1 over alpha.
Yeah, it's very good. Yes, it's a correct answer, but you have to take a fractional part of 1 over alpha, because you can imagine 1 over alpha is some integer, has some integer part. But yeah, you are right, almost right. It's actually minus 1 over alpha. We will see it, but yes, it is a rotation. One more time, it is a rotation. So if you induce a rotation on this interval, we will get one more time a rotation. Let me explain why. So look at this interval 0 alpha. Where does it go after one iteration? It goes to this next interval, alpha 2 alpha. And then after the second iteration, it goes to this interval, 2 alpha, 3 alpha. And then say it comes back and it kind of covers a part of itself. So we already have this orange interval, which was somewhere on I. Actually, it was on the end of I, which after 3 iterations came back, right? So here it comes back in the beginning of I, but in the beginning it was in the end, because it was like the forward point of I, which was moving first. And this yellow interval, of course, will be covered by the rest part if we do one more iteration. So what I'm saying is that this interval I is cut into 2 parts, one I1, one I2, and these 2 parts are just changing their order in this way. So you see that if you, so on my picture, the restriction of T to I1 is the 4th power of our rotation, and the restriction to I2 is the 3rd power of our rotation. And of course, in general, here you will have n plus 1, and here you will have n, where what is n? N is how much time you have to cut your circle into parts of alpha in the way that at some moment alpha crosses the circle. So it's related to the integer part, of 1 over alpha. So why this is a rotation? You see that if you glue the point 0 with the point alpha, so you take this interval and you glue the end point and the beginning point of your interval, this map, which seems to break something, actually doesn't break anything, because it's just a rotation. I1 is pushed to the left, I2 as well. And by how much they are pushed? By exactly the length of I1 to the left, or by exactly the length of I2 to the right. So the rotation is the rotation angle is not difficult to calculate. You have just to divide the length of I2 by the global length of your new interval. So the length of I2 is this interval. It's n alpha minus 1, because this point is n alpha, and we just covered one circle, so we have to take minus 1, and we divide by the global length of the interval alpha. So we get n minus 1 over alpha, but n is nothing with the modulo 1, so we get this minus 1 over alpha. So you almost guessed correctly, but you have this minus. But this minus is not very important, because you can change the orientation on your new circle and say that the map which really interests us is this map. The point alpha between 0 and 1 is mapped to the point fractional part of 1 over alpha, and this map is called Gauss map. So what I want to say is that this is exactly renormalization for rotations. What happened here for our dynamical systems? We have a rotation by some angle alpha, and by taking a first return map on a small interval, we get a new rotation with a different angle, which is fractional part of 1 over alpha. So we connect these 2 different rotations. But these 2 different rotations, you see that their dynamics are, because if I see some orbit moving on the interval, some orbit of t here, it's connected to the orbit which goes out and then comes back to t. So the orbits of the first and the second rotation are related. So yes, what I'm saying is that Gauss map defines renormalization for circle rotations. You have a circle rotation which can be associated to another circle rotation, etc., etc., etc. When renormalization is not defined, it's not defined when we can't come back to some interval. It's not defined only if we are not moving at all, actually, and when the angle is equal to 0, alpha is equal to 0. Let us look at some example. For example, if your rotation is of angle 11/16, so it's a rational rotation, then Gauss map, the first iteration of Gauss map, so I have to take 1/alpha, so it's 16/11. It's bigger than 1, so I get 1 out. I have 5/11. Then j squared of alpha is 1/5, so we have 11/5, and we take 2. And the third iteration of Gauss map is 0. So you see that after 3 iterations of Gauss map, we get to the moment when renormalization is not defined. And you see that in this way, we actually can prove that the map is completely periodic. It's maybe a little bit difficult way to prove that rational rotations are completely periodic, but that's kind of a way one can use renormalization to prove this statement. And you see that this Gauss map is also related to something which is called continued fractions. It's a representation of any number as this kind of big fraction. So you write 1 over something, then you take some number that corresponds to the integral part of something which is left, plus 1 over something else, etc. For rational number, this continued fraction is finite. For other numbers, it's not finite. So you see that the Gauss map is related to this fraction. And these numbers are, what are they? They're exactly the times you have to wait to come back to your interval, to kind of eat up all the circle for all the renormalizations. So they're also related to dynamics, to symbolic dynamics of your map. So as I said, when alpha is not rational, renormalization won't stop. Our induction will never stop because we will never get 0 rotation. And we will have this expansion of alpha in a continued fraction, infinite probably, and certainly infinite for a rational case. And this continued fraction algorithm is exactly the renormalization for rotations. You can take some time to think about this algorithm. It's very interesting and has many wonderful properties. I won't speak a lot about it because I'm interested to show you another example when we have a quadratic family. But let me show the graph of this map. It looks something like that, because Gauss map, as we have seen, it's a fractional part of 1/alpha. So depending on if 1/alpha is living between 0, 1, 1, 2. Okay, so let me resume from here. So what I defined this procedure, which is taking the first return map on some subinterval. And we have seen that on the level of the number of the rotation alpha, what is happening is this Gauss map, which is taking the fractional part of 1/alpha. And you can also see it in another way as an action on the continued fraction of alpha, which is this way of writing the number. Any number on the 0, 1 interval can be written in this form. And the numbers here, A1, A2, A3, etc., define uniquely your number alpha. And this is in some way a good way to write any number. Of course, we use some decimals, etc., but it's a really good way to write any number because the dynamics of this Gauss map sees this representation and not a decimal thing. I think continued fractions should be studied at school, but probably the problem with them is that it's very hard to add them, but they are the best way to write numbers for people who do dynamical systems. And we can see that the Gauss map acts on continuous fractions just by taking out the first coefficient here, A1. Why? Because Gauss map is taking 1/alpha. So taking 1 over this number is just getting erasing 1 here and just taking the number which is A1 plus 1 over something, etc. And then we take a fractional part, so we just throw away A1. So you see that we get a new continued fraction starting with A2, A3, etc. So it's kind of a left shift on the map, on the space of numbers. And then I told you about fixed points of Gauss map. In the language of continued fraction, it's very easy to see that the fixed point has to be such that all the A1, A2, A3 have to be equal to the same number. So it can be either 1, either 2, either 3, etc., any number n. But you can also find it as a solution of a quadratic equation. And the solutions of equations where n is any any natural number are exactly continued fractions of this way, of this kind, with all all these coefficients equal. And when n equals to 1, you get a golden ratio. So golden ratio is special for many reasons, but the real reason it is special, it's because it's a fixed point of this Gauss algorithm. So that was the slide. I hope I didn't lose neither mathematical, neither Wi-Fi connection with you. So let me ask if you have some questions or ideas about this this algorithm. The idea of this algorithm, I just wanted to give you an example of what renormalization is. Renormalization is a map which acts on the space of dynamical systems. Here it acts on the space of rotation, mapping some dynamical system, a rotation with angle alpha, to another dynamical system, a rotation with an angle 1 over alpha, fractional part of 1 over alpha. So as we have seen, for example, the system with rotation number 11 over 16 is mapped to a new system with rotation number 5 over 11. So please, do you have some questions?
There are some questions, indeed. There's a question from Dang Dang on your example on your slide with the circle. And the question is, for this particular R alpha, where's I1 and I2?
Yes, thank you very much for your question. Let me precise it. So for this drawing, what I drew here are not actually I1 and I2, but they're images under T. Look, you have an interval which maps then here. So the interval 0 alpha by the rotation of angle alpha maps here, and then it maps here. And then the fourth iteration is between 3 alpha and 4 alpha here. So this orange interval here, it's something that on this picture I call T of T of I2. Oh, sorry, I understand your question now because I actually used the wrong colors. So this is actually T of I2. So I should have drawn orange here and yellow here, but I got confused. So this is T of I2. And I2 is actually on the end of your interval. So I2 lives on the end of the interval, and I1 lives in the beginning. So it has the same length as this interval and lives in the end. So if you want this picture I drew here, you can draw it here. T of I2 is this interval. T of I1 is this interval. I2 is something living here, which has the same distance as orange interval on the picture on the left. And I1 is something which is living here, which is a pre-image of this yellow interval here. So on this interval, what you have an orange interval and a yellow interval, which are just coming back. The yellow interval comes back after 4 iterations. It makes tick, then here, then here. Sorry, it starts here, then it goes here, then it goes here, then it goes here, and then it comes back here. So it made 4 iterations. And the orange interval, it starts here in the end of 0 alpha, then it goes in the end here, then it goes in the end here, and then it comes back in the beginning here after 3 iterations. So I hope I'm clear now. So the problem maybe for you was that here I drew wrong colors. I confused the colors in this picture. So I hope it's clear, but you can also look for some concrete example. You take some alpha and write down what is this cut here. It's it's a good question to see.
Thank you.
So did I answer the question?
I see no further comment. It takes some time. So, yes, he says yes. Thank you very much. Or they say yes. Now there's a question from Dango Kui. Could you say more about the meaning of the word renormalization?
Say more about renormalization?
Yes. What does this word mean exactly? Yes.
So yes, with pleasure. My talk is about it. So in general, what does renormalization mean? It's a way to, if you have a class of dynamical systems, you have a map which maps one dynamical system in this class to another dynamical system in this class. So it's a very vague maybe definition. It doesn't always exist. Renormalization exists only for dynamical systems in some small dimensions, not very hard dynamics. It doesn't always exist. It's, in some sense, it's quite magical. For example, here I gave you one example for renormalization. It exists in some way. It seems magical, right? That you take some first return map and it lives in the same family you started with. So the existence of renormalization is always, in some sense, a miracle. And to find it, it can be some kind of art, not science. How to say? I have trouble giving the general definition because let me answer like this. If you have a dynamical system, you can find an intelligent way to choose a subset of your set on which you take a first return map. And if you have chosen wisely a first return map and you got very lucky, then you come back to you see one more time the system of the same class you started with. And this is renormalization. Renormalization is taking first return maps in an intelligent way. So let me speak about the second and the main example of my talk, and I hope it will be more clear what is a renormalization in this case and how it can be helpful. But of course, my goal is not to give you the full description of what renormalization is. For example, if you want to learn more of it, I can recommend an article of Arthur Avila. He wrote a good research article about this in 2010 for the ICM Congress of Mathematicians. Here he explains more general ideas about renormalization and how it works. Today, I would like especially to give you two examples and to explain you like Russian school way of explaining things. It's to give two non-trivial examples on which the main ideas of renormalization are clear. So the second example is the story of quadratic maps of the interval. It's called a logistic family. It has been introduced and popularized by the work of May, who was a biologist. And he was modeling a life of a population, of some population, say of bugs or butterflies. The idea is the following. You take a map which maps a point on an interval x to this product a, where a is some parameter multiplied by x multiplied by 1 minus x. The idea of why it models a population, the idea is that you have some number of butterflies, say x, and then they leave and they lay eggs to make caterpillars. And if there is not too many butterflies, then there is less food for every butterfly. So we have to multiply the number of butterflies by the number of resources, which is growing in this way with respect to butterflies. The more butterflies you have, the less resources you have. So when you iterate this map, when the butterflies leave following this rule for long years, what is the concentration of your population in the forest after a long time? So here A is just a parameter. If it's 0, you have a very unexisting dynamics. You just have 0 butterflies after 1 year. But if A is 0, you have this curve here. It's a parabola. And you have some dynamics. You can iterate it. You can take this, and then you take fa of this number, so you have some 4th degree function of x, etc. Why do I take a only till 4? Because you can see that the maximum of this parabola is always in 1/2, and when a equals to 4, it's exactly equal to 1. So in this case, the interval 0, 1 maps to itself. It's easier to work with this system, not to get out of the interval. Okay, so we are interested to study what happens with our butterflies. Let us look at some simple cases. Suppose that a is small enough. It's smaller than 1. Then the only fixed point of our little parabola here is 0. You don't have any other fixed points. So what will happen if we iterate the map? Take some x here. It goes here in this point. It's f of x. The next iteration, I have to take the intersection of this line with y equal x. So f of x, I have to come back to the abscissa axis. So it will be somewhere here. And you see that tick, 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 the iterations of our map will converge to 0. So whatever quantity of butterflies you have chosen, whatever concentration between 0 and 1 butterflies you have chosen, you will at some point kind of fall down to 0. So your population dies out. If it was concentration 1, so many butterflies in the forest that there are no resources for butterflies, they will die directly. If there is 0, you have nothing to start from. And if something in the middle, it will die after some number of iterations. It will be very, very close to 0. So there is no interesting dynamics. Population dies out. Now we change the parameter. We make it smaller than 1. What happens is that a new fixed point appears. It's a point 1 minus 1 over a. You just have to solve some quadratic equation. Okay, you can also calculate the derivative in this point. It's this number. So what it means, the derivative means how the tangent line in this fixed point here, so the fixed point is the intersection of this line y equals to x with your graph, how the tangent line changes. So you can see that between between 1 and 2, so when a equals to 1, you have the only fixed point is 0, and the tangent line is just y equal x. It just has this, the same direction as y equals x, and then the tangent line starts to move. When a equals 2, it becomes horizontal, and when a equals to 3, it becomes the derivative becomes minus 1, so it becomes orthogonal to the line y equals x. And in this range, when a is between 1 and 3, you can show that there is only one equilibrium. Actually, all of your dynamics will tend to this point. Why? Because, for example, if you have a between 1 and 2, what will happen? You have this tangent line, which is something like this. It's not yet 0, but it's bigger than 1. And any point, for example, which approaches here, it goes, you take f of x, then you come back to y equal x, and you draw this kind of ladder. So drawing a ladder is useful to see how the orbit goes. In the beginning, it was here, then it is here, then it is here, etc. So it approaches your fixed point. The same from the right. When a is between 2 and 3, the things get reversed in the sense that now your line, the tangent line, goes like that. So if I from my equilibrium point, I'm going to the right. When I was to the left and to the right, I will be going to the left. So you have to draw this picture of movement, and you will see that still you tend to an equilibrium, but you're not approaching your equilibrium from one side, but from one side, from another side, from one side to another side, etc. So what happens if you take some concentration of butterflies in your forest with this parameter a? Your concentration, little by little, will converge to some fixed point, which is 1 minus 1 over a. So you have one equilibrium. When you come back to your forest after a long time, you will see more or less the same number of butterflies for all parameters a in this interval. Okay, so we understood the behavior between 1 and 3. Let me jump now, forget what happens between 3 and 4, and just look at a equal to 4. A equal to 4 is very different from what we have seen. In this case, the map is chaotic. Let me explain, let me say what it means. It will mean that if you take some random population of butterflies in your forest, it will jump around on the population size and actually kind of fill in a dense way your interval. You won't stabilize your population won't stabilize at all. And if you take two different population sizes, you will have that after some finite and quite quickly, they will have very different lives. They will diverge a lot. So it's called butterfly effect when you have a very, very sensitive initial conditions. You are very sensitive to initial conditions. If you take population of butterflies somewhere here and somewhere here, after some finite number of iterations, one will live here and one will go here. So very different stories, even if you started very, very closely. That's what chaos means. Your small change in initial conditions change your life completely. And that's what will happen to our butterflies when A equals to 4. The explanation of this is to look at this map in another coordinate. Of course, it kind of comes from the sky, the change of variable, but you see that it's very useful because if you take x equals to sinus squared of alpha, some parameter alpha, you see that f of x is by some trigonometrical calculation with which you are familiar certainly to sinus squared of 2 alpha. So in some sense, it's just a doubling map. It's alpha goes to 2 alpha in this coordinate. So I just changed the coordinates. I didn't change the map. And in these coordinates, my map is just what we call a circle doubling map. If you draw it, the graph of this map, it looks something like this. Your circle is stretched by a factor of 2 and covers itself twice. So that's what you see here on the picture. And studying this map is very useful in a binary system. And you can see that if you write any point x as such a sum, so a0, where a0 is either 0 or 1, multiplied by 1/2, plus a1, which is also 0 or 1 multiplied by 1/4, etc., then the circle doubling map is only a shift, because you see that when you multiply by 2, this will not be useful because it will be either 0 or 1, so it's 0 modulo 1, and this will become kind of the needed a0 because 1/4 will become 1/2. And you see that the doubling map in these coordinates, it has the properties I told you about, because if you have 2 points which are very close means that they have the same beginning in this binary system. You see that if I write these 2 points, how close they are. The distance between them is smaller than 1 by 2 to the degree 1, 2, 3, 4, 5, 6 to the degree 6. So 64. So 2 points are closed by 1 over 64. And then after 6 iterations, they can be living in 2 different parts of your circle. So this map is very chaotic. In some sense, if you try to look at what set your points, your populations accumulate, it will be all the interval. So we say that the attractor in the sense is all the interval. It's very different from the cases we've seen before, when the attractor is just 1 point, either x0, either 0. So to summarize what May has shown, that he has explained actually some parts of this picture. So let me say what this picture is. Here on the x-axis, we are drawing the parameters A. Here it's written lambda, but it's our parameters A of our family, of our logistic family. On this vertical axis, we will draw the attractor. We will draw the equilibrium points for our butterflies who live in the forest. So we have seen that in the beginning, when A is smaller than 1, everything, the population dies. So the attractor is just 0, the point 0. Then we have seen that the attractor is a point which is 1 minus 1 over A. So we draw this hyperbola. This is a part of the hyperbola here. So I have explained to you these 2 blue segments. And I have also explained to you what happens when A equals to 4. It's not drawn here, but it will be all the segment here. So in the end of the picture here, you have to draw all the vertical segment from 0 to 1. This is a chaotic behavior. So these 2 parts. And then Mitchell-Fleckenbaum looked at what happens for other parameters, and he has seen this very, very complicated picture. So now I want to explain you why this fork appears when A becomes equal to 3. Let me ask you if you have some questions.
Yes, there seems to be some question. Here's one from Stjopa Charkov. On the slide where we replaced x for a sign, could you explain again what the sum on the right side of the page is, please?
This one, yes? Do you mean
yes,
this?
Exactly.
This
yes.
sum?
Yes, that's the one.
So, okay. So, okay, maybe I was very motivated to finish all the details. So on this slide, I wanted to explain you why this map is chaotic. The proof goes like follows. I choose a good coordinate in which the map looks like this. And then I want to choose even better way to looking at this map. In some sense, change the coordinate one more time and look at this map in this coordinate. So let's explain this coordinate. This is a way to pass to binary system. So for example, let's say your point is 3/4, 3 divided by 4. I want to say that in these notations, I will just write it 0.11 and then the 0, 0, 0, 0. So any point on your interval 0, 1 can be represented as this infinite or sometimes finite sum, which is the sum of numbers ak, which are either 0 or 1, multiplied by the inverse degrees of 2. You write any number in this way. You can do it because you see that it's kind of, you have to know how many, you see, like, for example, it's either in this first part between 0 and 1/2, either in the second part. If it's in the first part, A0 is 0. If it's in the second part, A0 is 1. For example, say we are in the first part. Then we have to know if A1 is 0 or 1. It's 0 if we are living in this between 0 and 1/2 or 1/4, and it's 1 if we're living between 1/4 and 1/2, 1/2. So you see that any point on the interval 0, 1 can be represented as a sum. We are kind of precising where it is by dividing the interval into smaller and smaller parts, dividing each interval by 2. So you have this representation. Why this representation is using to understand the circle doubling map? Because it's very easy to see how the circle doubling map acts on the sum. If I multiply the sum by 2 on the circle, this term disappears because it will be A0, right? And A0 is either 0 or 1 on the circle, it's nothing, because 0 is equal to 1 on the circle, right? Because it's the same point, they're glued. And A1 over 4, when you multiply it by 2, it will give A1 over 2. So it's kind of a new A0 for your for the image of your point X. So the point like written like this is mapped to the point written like this. That's what I was trying to say. It's the circle doubling map is just a shift, but in this good coordinates. You shouldn't confuse this with a decimal representation. It's a binary representation. So it's the same as decimal representation, but in decimal representation here we write 10, 100, 1000, etc. But here you write 2, 4, 8, 16, etc. And you can see that circle doubling map is very, very sensible to initial conditions, because if you have 2 points written in this way, then the moment they are different, it comes very fast for the circle doubling map. You have only to apply it some number of times, right? So, but the points in this representation, if they have the first n symbols the same, they are 2 to the power minus n close. They're very, very close. So this is what explains the circle doubling map is chaotic. So I hope I'm clear. Please tell me.
I think so. From the comments, I can select the phrase, "This is genius." I think this really answers the question.
Binary system is genius, my friends. There is even an anecdote like this. There are 2 kinds of people. No, sorry. There are 10 kinds of people. Those who understand binary system and those who don't. You can tell it. It's only funny for people who do understand binary system.
Thank you.
Okay, it's better written, but anyway. Okay, so let us come back. Logistics. Do you have some other questions?
There are some others.
I'm okay if I.
Okay, maybe I can ask one more from Hoang Nguyen. No, I apologize. This one, yes. So from Han Nguyen, can we always choose a quote unquote nice way to represent maps?
No, not always, not always. But there are many. I mean, there are many. Of course, there are many definitions to nice in mathematics. What is nice? You can say that something is nice when you can understand better. So in this slide, of course, this is a very nice way to understand, and it seems like a miracle, and we understand everything. You see that the map class of maps I'm describing to you, we understood the behavior for a between 1 and 3. You understood it for a equal to 4, but the maps I will speak about now, it's much more complicated. It's much more complicated because in some way we don't have a nice way to understand one map, but we have a nice way to understand all the maps at once. So yeah, the quick answer is not. Otherwise, we wouldn't have things to do because there will be nice and clear ways to do anything. But when we do, we can say more. So of course, trying to find good weekend coordinates for some map is a very noble goal. But you always have to keep in mind what is your question, what you are interested with. Yeah, so no, I mean, this kind of magic, it happens for a equal 4, for example, but you see that the way it happens here, you are using the properties of sine and cosine. If you change this 4 by 3.5, it won't work, right? So we have to do something else. Okay, so now let me explain to you what happens here. So you see, we had one equilibrium, and what this fork means, what it's supposed to mean, is that now we will have for each a between 3 and some, between 3 and some other number, is that we have 2 points which are in the tractor. So we have 2 different equilibriums for our butterflies or our bugs or whatever you want. So how does it happen? So it's a little bit more complicated, but you can also see it on the graphs of your function. So let me draw what happens. So for a equals to 3, we have this graph, still a parabola, with the high point at 3/4 here. At x0, you can calculate it, but it will be exactly -1. So the tangent line is like this. It's orthogonal to y equals to x. And you see that when a passes 3, it seems nothing happens with f. I mean, the tangent line will become even lower like this, but we don't see any change in behavior. Changes in behavior in dynamical system, we call them bifurcations. Something drastically changes. The behavior changes completely. We don't see it here, but we can see it on another picture if you take the f squared. So we don't take f of x, we take f squared of x. So here you have to write to apply this twice to x. So it will be something like x1 minus x multiplied by 1 minus all this thing. So I drew its graph here. 3. Which points are here the maximums? You have to see what points goes to 1/2 after one iteration. You will have 2 points like this, and this will be the maximums. And you have this graph like this. And it happens then, since you have x0 is a fixed point, then the derivative of f squared is exactly 1. It's not always true that the derivative of f squared is equal to the square of the derivative of f, but it's true for the fixed point. So here you have that the f squared is tangent to your line. It kind of goes up the line and then it goes under, and it's tangent to this line. And you have no other fixed points for f squared. You have only one fixed, you have 2 fixed points. You have 0 and you have our x0, which is a fixed point for f squared and for f. But what happens when you move a little bit more your parameter? What will happen is that this green line will turn and will become a little bit more vertical. So let me show it here. So you have this tangency here. Okay, pictures are not very, I'm sure those of you who are interested in programming, you can very easily program a graph of this map. You see that if a is a little bit bigger than 3 plus epsilon, this tangent line, which is y equals to x, goes a little bit more vertical, and your new 2 fixed points for f squared are created. There are no new points, new fixed points for f, but there are no two new fixed points for f squared. But what are fixed points for f squared? This have to be necessarily the two periodic points for f. So this point goes here under f, and this point goes here under f as well. And you have two fixed points for f now. So what happens now is that from this picture, well, all the dynamics of f was falling on x0. So it was true for any a between 1 and 3 included, as we have seen. When a is a little bit bigger than 3, 3 plus any epsilon you want, any positive epsilon you want, so like 3001, but also 300001, your red point will not die. It would move on a little bit, but it won't die. But it, instead of being a stable equilibrium to which all the butterfly populations tend, it will become unstable, but it will create a stable cycle of 2 points here. You can see that they're stable by doing the same argument we did before by kind of drawing the ladders. So what happens, and then next year have x plus butterflies, etc. So it's like this infinite cycle. And for another trajectory, you are approaching this infinite cycle from different sides. So you're kind of converging to this alternate behavior. You have either 3 butterflies every year or 7, and you're changing like this. Okay, so this is what happens when A is a little bit bigger than 3. You have this attracting 2 orbit instead of 1 equilibrium, which is already quite impressive. So what I did now, I explained this fork here, this first fork. At some moment it will stop. So I promised you that there will be something much more complicated. And what I will explain is that actually you have not only one bifurcation of this time, but how we say a cascade of bifurcations. This is the first time the bifurcation happens, and you will see more. So yeah, questions time. Did you follow this step for A bigger than 3? And do you have some questions?
There were a few seconds where we couldn't hear you, but it seems that this was quickly solved, and now we can see you again very well. I disappear again. Are there any questions, please?
So you see, it's already a little bit funny behavior. We had one attracting point for all our possibilities of initial conditions, how we start, and now we have 2. Actually, we have 2 attracting points. We have an orbit and 2 orbit, which is an attracting point. So now our stable behavior is. So as I said, that's not all. So for now, we have seen that for A from 3 at A equals to 3, something happens. There is a fork that appears, and actually it will continue like this till some new moment, which is somewhere around 345. So this is very approximate, but it can be calculated very precisely. What happens here? So now instead of looking at the map F, initial map F, which looks like this kind of hole, like a parabola, we look at F squared. So F squared for our map, we know that it has 4 fixed points. These 2 points correspond to our 2 periodic orbit, and this point and this point correspond to fixed points of F. You see that fixed points of F to some power n, they're either fixed points of F, either they're periodic points of F. And now I want to see the same thing, the kind of doubling, period doubling bifurcation, as we call it, for not for F, but for the F squared. So for this, we take the graph of F to power 4. This is much more complicated graph. It goes something like this here in violet. And you see that we have this 3 intersection points here. And we look at this point. So this is a fixed point for F squared. This is a fixed point for F fourth. And at some moment, when you change the parameter A, when A becomes bigger and bigger, you will have that the derivative will be 1 more time equal to 1. And then the next moment, what will happen here? There will be 2 new points which are born here for which are fixed points for F to the power 4, and which are a 2 periodic orbit for the F squared, and which are hence giving a 4 periodic orbit for F, initial F. So we have 1 more time a period doubling. What happens is that what we had before was a 2 periodic attracting orbit, each of these 2 points stops being attracting, becomes repulsive, and there is a new quadruple of points which is born, which is attracting. So the new picture is like this on the interval. You have 4 orbit of points which are attracting, and all your butterfly populations are converging to the cycle, etc., etc. So what happens now is that you have these forks which appear. So this is your 2 periodic orbit, and it makes babies, which is a 4 periodic orbit here, etc., etc. So you have an infinite number of period doubling bifurcations here, which are these 4. So I have explained that we have this infinite cascade of bifurcations. And now let me formulate some kind of a miracle. So the first thing is that we have this cascade, that the parameters A for which the cascades happen converge to some number which is smaller than 4, which is equal to approximately to 3.57. And the miracle is the following, that if you take these intervals here and you take the ratios of their lengths, these ratios are actually approaching this the same number, which is delta, which is called Feigenbaum constant. So it's geometrically growing slower and slower. The new points appear closer and closer to A infinity in a geometric sequence. So you have this an minus 1 is proportional to some constant multiplied to delta to power minus n. But what is even more surprising, that there is some kind of universality called Feigenbaum-Collet-Risset universality, that this delta doesn't actually depend on the family. What it means is that it doesn't depend on the law you have given for the life of your butterflies. We have been working with this family all the time, but now I want to say to you that if you take any family which looks like this, any family of maps, 1 parameter maps, which look like parabolas in the sense that they grow up and then go down with like 1 turning point, this is a mathematical miracle. So it has to be explained, and it was explained, and there were many works. This the idea is like this is the one thing to get from this talk, is that there is this phenomenon of universality, that the bifurcation moments, the differences between bifurcation moments are governed by butterflies in the forest. So this is the first thing to take out of the talk, is that this is a very surprising, completely non-trivial kind of miracle. And the second thing to get out of the talk is that this miracle can be explained because of the renormalization. And the idea is the following, that let us look at our map F. We have seen that the map F squared has something like this, looks something like this, right? It has 2 maximum. Here is the local minimum like this. It looks like this kind of graph. So the idea is the following, that as before for circle rotations, we will choose some small subinterval here, which is corresponding to one left point of the square and right point of the square. And we will induce the dynamics on this interval. I won't explain in details how it's chosen and so on, but what I want to say here is that if you take a first return map as before on this interval, you will get some map which resembles a lot an initial map. So it's not the same map, but it is also unimodal. It also has the same, more or less the same form. So what you do here, you take a first return map, not of F, but of F squared. It's an important technical detail. So you take a first return map of F squared, but of course the dynamics of F and F squared, they're related a lot. So we can understand the dynamics of F by understanding the dynamics of F squared. And you see that the first return map of F squared on some smaller interval is in the same class as F in the beginning. So the class now is not our family AX multiplied by 1 minus X. It's all the maps which look like this, which have the graphs which look like this. They're going up and then they're going down. But you imagine there are many of them. I give you 2 examples for this, but you can draw any line you want here, which is smooth enough as you want. Renormalization acts now not in the space of maps of our kind, ax multiplied by 1 minus x, but in much bigger space. But still, understanding this renormalization will help understand us the universality phenomenon. See the map that resembles your initial map inside your map. And okay, we reduce the problem to the problem of the same kind. But the idea is that the renormalization operator is in some sense simpler to study than the initial dynamics. So let me say one thing, that first, this renormalization map, which I didn't completely define, but I tried to give some idea of it, it has a fixed point. It means that if I take some first return map here, I can manage to find some map, very, very special map F, Piggenbaum map it's called, such that the renormalization of its map, this map is exactly itself. So we come back exactly to the picture we had in the beginning. So here I write it as F star. So here it's a little bit complicated slide. There are many difficult words. I don't expect you to understand it perfectly, but it's just to give you an idea of how modern mathematics looks and what are the ideas in it. So you see that this theorem is by Lanford in 1992, and Lubitsch gave another proof using other techniques, complex techniques. So the theorem is the following: that the renormalization operator, in this case, has a fixed point, and it is hyperbolic dimension in the space of functions. It's a very, very big space. It's not 4-dimensional, it's not 5-dimensional, it's infinite dimensional space. So it's hard to imagine, it's hard to get inside our head. But have this mental image in mind. Think about such a map, which is a map of R3 to itself. So where did I lose you on this theorem I am on? Or before?
Yes, you were explaining the theorem of this one exactly, of Lanford.
Yes.
And Lubitsch.
So this is to give you a taste of modern mathematics. As I said, I don't know if you heard me. It's really not to you to get all the details, but only just an idea of what happens. Renormalization operator, this renormalization I tried to explain, acts in the space of functions, of the space of maps. It's a very big space. It's an infinite dimensional space, because you can take many different families. You can take quadratic families, sinus families. It's a very, very big space, but you still have a fixed point, which is some map, which can be described. And you can think about this map in the very, very big space to have this mental image of it. As it was a linear map, as it were a linear map of three-dimensional space, which expands the z-axis and contracts along x and y axis. So you have this kind of behavior. Everything is kind of coming to the z-axis and then going up or down with respect to it. We see that if we have a fixed point and the renormalization operator is hyperbolic with one-dimensional unstable direction, which means exactly that it looks more or less like this map. So you think about 0 here as our function, which is a function from 0,1 to 0,1, which is a fixed point of your renormalization. If we prove this theorem, I don't tell you how to prove this theorem, but this is a theorem proven, you see, not so long time ago. Most probably you have not been born, but your parents have been born. This theorem, it's not really so surprising, because if you take some map like this, it has good chances to have some directions which are contracting, some directions which are expanding. It can be, and since we see the phenomenon of universality, actually, it seems not surprising that the unstable direction is one-dimensional, but we have to prove it, and it's a hard work to prove this theorem. But once you have proven this theorem about the renormalization, you can prove this universality phenomenon. And the sketch, the idea of the proof is that, okay, we are in this big space. It's a space of our functions. So for example, our dynamical systems are points, yes? So for example, one red point here, it's some system, for example, ax multiplied by 1 minus x for some a. So, so if you change a, you have a line like this, a curve in your space of functions. And you see that the green one here, it's a place where the period doubling happens. And for our map F, where is the hyperplane where the period doubling happens for f squared? This is the question. You see that, for example, here the red point here, 3x multiplied by 1 minus x. This is a point for our family where the period doubling happens. For the sine family, maybe it will be some other point. But the period doubling for f squared happens. We know it happens at 345 for us. But the important observation is that it's exactly the pre-image of our plane, which is actually, you can think about it as a plane, which is a pre-image under renormalization. So you have this family of planes which come further and further to this red plane, and your parameters A1, A2, A3 that we defined by this infinite number of renormalizations, they're just intersections of your curve with this fixed family of planes, right? So you see that the distances between A's, and if I drew another curve B, right, which is traversing all of our infinite family of planes. So I drew only two of them, but there are many which approach the red line, which correspond to period doubling for F4, F8, etc. The intersections, the distances between them behave in the same way, because we just intersect an infinite number of planes which are converging to some fixed plane by different curves. So the distances behave more or less in the same way, and their behavior is governed by the way how this unstable direction is expanded, right? It's governed by this number, and this number is exactly delta. So probably I'm not clear here, but it's to give you a big picture of the fact that this number delta for different families is the same, because you have this global dynamical system, which is called renormalization operator, for which this delta is a very important parameter. It's just the parameter of expansion of this direction, which is, in my simple example, it's 2 here. It's 2z. Here it will be delta, right? So this is an idea that this delta is hidden somewhere in renormalization. So it's very useful to prove something about some particular families. So let me give 3 final remarks about this picture I've shown you. That I tried to explain what happens till this A infinity. What happens after? It's a complicated story. One needs more time to understand it. Results of it are results by Lubitsch, and are very important results. I can just say that different behaviors for different parameters A can be possible. Some look as A equal 4, as I said, as are chaotic, and all the interval is filled. Some look a little bit as A infinity. They have an attractor which is not a finite set of points, but which is some kind of counter set of measure 0, of not necessarily measure 0. Some are behaving as this place on the forks, so everything falls on a finite number on a finite orbit. And there's something else, but this something else happens very rarely. Actually, this case also happens very rarely. So many different complicated behaviors can happen. So as you see here, it's not only like this, and not only all full interval. Other things can happen. And Avila and Lubitsch studied this kind of questions for higher degree polynomials. So we studied for 90 minutes. We studied degree 2. You can also study degree 3, 4, and results exist. And Avila was awarded a Fields Medal in part for this work. So it's very difficult in modern mathematics. It needs time to be understood. And let me say the last thing is that it's related to famous Mandelbrot set that you see here on the right, which is related to complex dynamics. In some sense, it's related to the sizes of this let's say, circles here, and their sizes are exactly the sizes corresponding to the numbers a1, a2, a3, etc. And the idea is that the renormalization I defined for quadratic family on the interval can be actually also prolongated to complex domain for the quadratic family in the complex domain, for those of you who know the Mandelbrot set. So Mandelbrot set is related to the picture I discussed today, to this bifurcation picture. So you see that the techniques we discussed today seem coming from the real world, but actually they come from the complex world. And let me also say that I gave you two examples, renormalizations for rotations and renormalization maps, but they exist for many other classes and situations of maps, usually in low dimensional dynamics, and there are reasons for that. So don't think that there are only two examples of renormalization. There are many others, and as I said, it's like one of the main tools in dynamics today. I even have a collaborator who says that the only thing we can do is to renormalize. So it's just to give you the idea how rich the dynamics of maps of the interval or of the circle can be, and what are the methods behind this richness, and what are the things behind this richness are actually maps in some infinite dimensional spaces, but which are maybe paradoxically easier to understand than the simple maps of the interval. And it's because of these maps that we are able to understand the simple and humble maps of the interval, because we have this renormalization maps in infinite dimensional spaces, which are hyperbolic, but are simpler to approach than this poor little map of the interval. Yeah, so this is, I think, the end of my talk. Yeah, of course, I didn't speak much about what happens here. Let me just say that I didn't tell you about all the renormalizations. I told you only about kind of two renormalizations. F goes to F squared, goes to F4, goes to F8. There is a hole here, and this hole here, they kind of correspond to three orbit, to the orbit with 3 points. And there are other branchings like this further in the system. Some we don't see. There are holes, but they're too small to see. And Yuri told you about Sharkovsky theorem, and there is some Sharkovsky order here on these branchings. I won't tell you about it, but the renormalization I told you about it is only one of the big class of renormalizations. Here, renormalizations actually can be done for any order. I explained you only renormalizations of order 2. So the picture is even more complicated than I told you about, but I hope I gave you a flavor of ideas, and I hope you will look at it more precisely and maybe draw this picture yourself. This you can do. You can think about how these pictures can be drawn, and I think you have all the tools to draw them yourself on your computer if you like doing this kind of simulations. So to conclude, let's say that I gave you two examples of renormalization. I didn't give you a general lecture on renormalization, but I hope it gives you some taste of what one can do in low-dimensional dynamics today. And that also gives you a taste that mathematics is not finished, that there is lots of things to do and to understand. Thank you very much, and please ask me some questions if you have more of them.
Thank you very much. Before asking any question, please let us thank Olga Romaskevich for her beautiful talk on renormalization.
Thank you, Pierre.
Thank you very much. And thank you for
problem.
No problem. Thank you for giving this talk from all the way from Siberia. So there are some questions. So here's a question from Dang Dang. For chaotic systems, does bifurcation always happen?
Okay. Okay. So let's look at this slide. So you see that to each number here on the horizontal line, you have a system, right? For example, for e equals 1, you have a system. For equal 2, you have a system, etc. And this system is not at all chaotic, because what you have here is that you have a map that after some long time, any point comes close enough to some fixed point. This system is not chaotic at all. Everything is attracted to one point. All the points, close points, have very close futures. For a equal 4, as I said, the system is chaotic. There are some parameters for which the system is chaotic. But in general, in family, if you take some a, there is a positive measure, the positive probability that you will have a non-chaotic system. You will also have a positive probability to have a chaotic system, but when the parameter changes, you can have chaotic or not behavior. It's very interesting and rich here, because for some parameters the system is very simple. For some parameters it's very difficult, and actually being very difficult in some way means that maybe it seems that you can renormalize infinitely, but I didn't say that actually for some of the maps here, the renormalization will stop. And for chaotic maps, actually the renormalization has to stop at some moment. Because in some sense, if you are able to renormalize and get something interesting, the complexity of your system has to be low, because if you are renormalizing and for a renormalization process to converge, you don't have to augment the complexity of your map. So let me say like this, that bifurcations occur when systems, you have some parameter, so you have not one dynamical system, but a family of dynamical systems, and your dynamical systems are different one from another. Some are simple, some are chaotic maybe. And this is where bifurcations happen. So in some sense, bifurcation and chaoticity are not necessarily related. You can also have bifurcations in families where there is no chaos. But for the example we have looked at now today, we have the systems which sometimes are very simple, non-chaotic, and sometimes are very chaotic, and they all live in the same family. And finding the points A here, which correspond to simple behavior, kind of, it's a little bit boring behavior, right? Everything goes on the same periodic orbit. Or chaotic, they are very intricately placed on the interval 0, 4. And as I said, there are also other types of behavior which are counters, like the sets here, they can be intervals, but there can be smaller sets, and the sets that have many holes, so many holes that they have actually zero measure, zero length, if you want. So the dynamics here is very different for every parameter. It can be simple, it can be chaotic. But what is funny is that the renormalization itself is chaotic. The renormalization itself is a system with high complexity. So in some way, you reduce one parameter system, one parameter family of dynamical systems with different behavior to one system which is chaotic. But understanding this one chaotic system helps you to understand the bifurcations in this family of systems which are different, and some of them simple. But yeah, but in general, chaoticity and bifurcation are not necessarily related. Bifurcations is just changing in the behavior. It can be not necessarily chaotic behavior. Yes, I hope I answered the question.
Thank you. Before I go on to the next questions, there are some comments also in the question box that I see. For example, thank you for this inspirational lecture. Despite the connection problems, this was my favorite talk so far, and so on. So there's several comments like this. There's several more technical questions now. Here's an example from Dang Go Kui. If A is greater than 3, but we let X start at 1 minus 1 over A, will it be stable at 1 minus 1 over A?
Okay, let's see. Yes. So you start your x before here in this picture, and you take a bigger than 3, and you are interested what is the future of the point here. So no, not necessarily, because you see, if you take, for example, x somewhere here, even for this case, so a equals 3 plus epsilon, take x somewhere here, it's smaller than x0, it will already have some, it will, in this case, it will fall down on x minus, but it doesn't have necessarily going, it's not necessarily going to 0, right? It's trapped because x minus stops it from going to 0. So the behavior is interesting till x minus, and when you have even more bifurcation, it will be interesting even further and further and further, and close to 0, the behavior can be interesting. So you see that it's kind of spreading to closer to 0, the behavior of our system.
Thank you. I think this may have answered also another question, which I'll ask anyway, from Alexander Korotkov. What happens with the first fixed point x0 when a is equal to 3 plus epsilon?
Yeah, so yeah, it's a good question. So the point x0, we have, of course, x0 changes when you change a. It's always 1 minus 1 over a, right? So it moves if a is bigger, is getting bigger and bigger. It's going further from 0. So it's going closer to 1. So it moves, but we could say that maybe it will disappear at some moment. Like maybe 0 disappears, something happens, but what happens is that in this cascade of bifurcations I described till a infinity, x0 is preserved. The explanation is that once it appeared, you have some derivative in it, and when you do this bifurcation, it's actually, it will be, once it's repulsing, you can see that it can, after another bifurcation, it will be even more repulsing, and it will be still present. So in some sense, this behavior x0, it doesn't change. You will still continue expulsing everybody from your neighborhood if you x0. Of course you move, you get closer to 1, but on this, you see that on these pictures I draw x0, but I should have written x0 of a, because x0 changes when the parameter changes, but its nature doesn't change. It will, once it becomes a repulsive point, it will stay. So I hope it answers this question.
Thank you. Another question from Enzo Marto. I remember hearing that there's a second Feigenbaum constant represented by the letter alpha. What is its relation, if any, with the things that we saw in this lecture?
Okay, I'm not a great specialist of it, but let me have a guess. I think it may be the ratios of this holes. So you can also look at them. You have to check it. I'm not sure I'm telling the truth, but I think that these are the ratios of the hole. So you have a hole here, the distance between two attractors in the end of the bifurcation, and have you distance here, and then you have the distances, and the ratios of the distances are also universal. So maybe this is called second Feigenbaum constant, but better fact check it. Fact check me somewhere. This is a in some way quite a famous subject, because it's very beautiful, and it shows universality. Sorry, I lost my slides maybe. So I think you will be able to find information on it quite easily.
Thank you. There are more questions. On this diagram here, a question from Dang Dang. Why did bifurcation happen at some or certain alphas?
Why did they happen here?
I think this may be the question, yes.
Yeah, so the explanation is this picture. So it happens when for example, for a equals to 3, I tried to explain it. Maybe I wasn't clear. So the bifurcation happens when there is a from one, so here you have one attracting point, which is this point 2/3, and when a is a little bit bigger than 3, what the graph of f squared changes its form, and it becomes something like this. So it was tangent to this line, y equals to x, and then it changes its form, and it gains 2 more fixed points. So this happens when, for your map f, the f squared derivative at x0 equals to 1. And this is a formula, an equation. So if you solve it, it's like a cubic equation in x, and you can find a for which this happens. If it happens, you have a bifurcation, and you have a 2 periodic orbit which is born, and your behavior changes drastically. The behavior of your map f changes drastically. Now your points are not converging to one point, but are converging to an orbit of 2 points. Kind of this point jumps here, and then it jumps here, and then it jumps here, and like there is some kind of a cycle here. So the behavior changes in this way. The next bifurcation will happen when the fourth iteration of your map will have a derivative 1 in the fixed point for corresponding to f squared. So this fixed point corresponds to, we now have this 2 periodic orbit, and there is a new bifurcation when these 2 points corresponding to this 2 periodic orbit have one more time, you have this birth of little 2 periodic orbit for f to the power 4, etc., etc. Because then you have a 4 periodic orbit, and you look at f to the power 8, etc. So these are the equations. Instead of 4, you can write 2 to the power n, which will define you this aj's. So the explanation of why the bifurcation happens is because the form of the graph of f to some power here 2, 4, or etc. changes in such a way that it starts intersecting y equals to x, and hence you have new periodic points which are born. And before, the graph moves in a way that, okay, it moves, but it doesn't change qualitatively the behavior. You see, for example, before a equal to 3, okay, this point was a little bit, this thing was going a little bit lower, this thing was going a little bit lower, this direction was not 1 but a little bit more inclined like this, but the qualitative nature of the dynamics didn't change. So it changes in this points. So of course it's not easy to see like from scratch, but once you understood the phenomenon, you can see it. But you actually also can see that something like this can happen if you look at f to the power 3. So there are other renormalizations. This is not the only way to change the dynamics. So yeah, I hope I answered the question.
Thank you very much. Yes, I think so. Another question from Stjopa Žarkov, who says that it might have been said, but because of connection problems, it might not have been caught. What exactly is the constant that appears everywhere? Is it the ratios between the lambdas, and what would it be for other functions?
Yes, so the Feigenbaum constant, the Feigenbaum constant is the following constant. Let me show the slide where I have written it, I hope somewhere. Here. So you take let's say we take A2 and A3. How much was A2? A2 was 345. A1 was 3. A3 is 35544. So let's look at the differences. A2 minus A1 is 0.45 more or less. A3 minus A2 is 0.9 more or less, right? So the ratio between those two is A3 minus A, let's say A2 minus A3 minus A2 divided by A2 minus A1. It's 9 divided by 4.5. No, wait, I did some mistake here. It should be around 5. 0.45, and the next difference is 0.09. Yeah, 0.09. So if I divide A3 minus A2 by A2 minus A1, it's more or less 1/5. So the ratio between the first interval and the second interval is 5:1, right? And then what I say is that the second to the third is something else, etc., and this ratio it converges to this delta, which is not 5 but close to 5, 467, and this constant is calculated very precisely up to 100 digits, and this is called Feigenbaum constant. So on the picture, you have to take the ratios of these intervals. What I calculated, that is the ratio of this segment, of the length of the segment, A2 minus A1, to A3 minus A2 is more or less 5. And what I am saying that the ratio of A2 minus A3 to A3 minus A4, it's closer to 4.67, and in the limit it's exactly 4.67. And this thing is not depending on the family. If you take another family, the ratios will also converge to 467, etc. And this is Feigenbaum constant. The moments in which bifurcations happens are dispatched in a way which is converging to this relationship, like a geometric sequence. They look from far away as a geometric sequence with this coefficient.
Thank you. And one last question for this question session, a question that was asked by several people. So I will try to formulate as general a question as possible. Could you suggest some good textbooks or references at undergraduate level on this topic or on dynamical systems?
Oh my God, I wasn't prepared to this question. Let me think. Okay, I feel very bad. I can't answer this question. I think it's awful. What I will do, I will think about it, and I will contact you, Pierre-Guy, and I will send you some list of references. Of course, I mean, for myself, I read some things about dynamical systems, and actually more classic. I started with classical way. I read Arnold book on which called Classical Mechanics, something like this, and differential equations, which is an introduction to this subject. But I think it's already further than undergraduate level, yeah, it's very hard to me to say. I'm very sorry, because I learned a lot by talking to some people, and I think it's also a good way to learn. It's exchange with people you know. For example, if you have some questions and you want to discuss, just write to me an email, and I will try to tell you where to look in more precise directions you are interested in. But for general suggestions on dynamical systems, I know this question, and I will make a list, and I will send it to you till tomorrow, so you can have it. And I'm very sorry to be completely out of concentration with your question. Yeah, it's been a long time. I haven't been an undergraduate, and I forgot on what books I learned. But I will. This will come back to me. I promise.
If you send us a list, we'll put it on the forum on the website of the school, of the summer school.
Yeah, I will try not to make a very long list, but I will try to make a short list of my favorite 3, let's say, what I would recommend to start.
Thank you very much. Well, this concludes the question session. Thank you very much again, Olga Romaskevich, for your very inspiring lecture.